Introduction to clay minerals. Clay minerals are a group of hydrous aluminum phyllosilicates that form an essential part of the Earth's soil and sedimentary systems. They are fine-grained, often microscopic minerals that result from the chemical weathering and alteration of primary silicate minerals, such as feldspars, micas, and volcanic glass. Despite their small size, clay minerals play a significant role in various geological, environmental, and industrial processes due to their unique physical, chemical, and structural properties. The structure of clay minerals is characterized by layered arrangements of tetrahedral and octahedral sheets. The tetrahedral sheets are primarily composed of silica tetrahedra, whereas the octahedral sheets consist mainly of alumina or magnesia octahedra. These layers can be arranged in different ways, giving rise to various types of clay minerals, such as kaolinite, montmorillonite, illite, and chlorite. Each type exhibits distinct properties, such as cation exchange capacity, swelling behavior, plasticity, and surface reactivity, which make clay minerals highly versatile. Clay minerals are integral to soil fertility, as they can retain water and nutrients, thereby supporting plant growth. In sedimentary geology, they act as indicators of depositional environments and diagenetic processes, providing valuable information about past climates and geological conditions. Additionally, clays are widely used in industry for ceramics, cement, drilling mud, paper production, and even in environmental applications, such as pollution control and waste containment. Formation of clay minerals occurs through a variety of processes, including chemical weathering, hydrothermal alteration, and diagenesis. For example, feldspar can chemically weather to form kaolinite under acidic and moist conditions, while volcanic ash can alter to smectite in the presence of water. The mineralogical composition and behavior of clays are influenced by factors such as pH, temperature, pressure, and the presence of organic matter and ions in the environment. In summary, clay minerals are not just fine-grained components of soils and sediments, they are dynamic, multifunctional minerals that bridge geology, chemistry, environmental science, and industry. Their study is essential for understanding soil mechanics, sedimentology, mineralogy, and numerous industrial applications, making them a cornerstone of both earth sciences and applied sciences. Formation processes of clay minerals. Clay minerals are primarily secondary minerals, meaning they are largely formed from the chemical and physical alteration of pre-existing primary minerals. Their formation is controlled by a combination of geological, chemical, and environmental factors, which influence the types, textures, and structures of the resulting clay minerals. Understanding the formation processes of clay minerals is crucial for applications in geology, soil science, and industry. 1. Weathering of primary minerals. The most common formation process of clay minerals is chemical weathering of silicate minerals, particularly feldspars, micas, and volcanic glass. During weathering, these minerals interact with water, carbon dioxide, acids, and other chemical agents in the environment. Hydrolysis is the dominant reaction in clay formation, where water reacts with silicate minerals to break down their crystal structure. For example, the weathering of feldspar produces kaolinite. In this reaction, potassium feldspar, orthoclase, is converted into kaolinite, releasing soluble silica and potassium ions into the surrounding environment. The resulting clay minerals are fine-grained, often layered, and capable of retaining water and nutrients. 2. Hydrothermal alteration. Clay minerals can also form in hydrothermal environments, where hot, mineral-rich fluids interact with rocks. These fluids often circulate through fractures and porous zones in volcanic or igneous rocks, altering their mineralogy. For instance, smectite and illite commonly form from the hydrothermal alteration of volcanic glass or feldspar. Hydrothermal processes are especially significant in the formation of phyllosilicates in or deposits, where they can influence the mobility and concentration of metals. 3. Diagenesis and burial alteration. During sedimentary burial, clay minerals can form through diagenetic processes, which occur after deposition but before metamorphism. In this stage, temperature, pressure, and the chemical composition of pore waters drive the transformation of unstable clay species into more stable forms. For example, smectite can gradually transform into illite with increasing temperature and potassium availability, a process known as illitization. Diagenetic clay formation is important in understanding petroleum reservoirs, as clay minerals can impact porosity, permeability, and fluid flow. 4. Volcanic and aeolian deposits. Volcanic ash and tephra are highly reactive materials that often alter into clay minerals upon exposure to water and atmospheric conditions. This process, called volcanic alteration, produces minerals such as montmorillonite, a type of smectite, in tough layers. Similarly, wind-blown, aeolian, deposits, including fine dust and loess, can undergo chemical weathering over time, contributing to clay formation in soils and sediments far from their volcanic sources. 5. Pedogenic processes. Clay minerals also form in soils through pedogenesis, the natural process of soil development. In humid and tropical climates, intense weathering breaks down primary silicates, and leaching removes soluble ions, leaving behind secondary clay minerals such as kaolinite and gibbsite. In temperate regions, illite and smectite are more common due to moderate weathering. Pedogenic clay formation is critical in agriculture because it directly influences soil fertility, water retention, and nutrient cycling. 6. Factors controlling clay mineral formation. The type and distribution of clay minerals depend on several environmental and chemical factors. Parent rock composition, silicate-rich rocks like granite, basalt, and volcanic glass are primary sources of clays. Climate, temperature and rainfall influence chemical weathering rates, dictating the type of clay formed. For example, kaolinite is common in warm, humid regions, while smectite is typical in semi-arid climates. pH and ionic composition of water. Acidic conditions promote the breakdown of feldspars, while cations such as K, Mg2, and Ca2 can stabilize certain clay structures. Time. Longer exposure of rocks to weathering increases the degree of transformation and the formation of more stable clay minerals. In summary, clay minerals form through a variety of interconnected geological processes, including weathering, hydrothermal alteration, diagenesis, volcanic alteration, and pedogenesis. Each process produces clay minerals with distinct chemical, physical, and structural properties, which are vital in soil science, sedimentology, industrial applications, and environmental studies. The study of these formation processes provides insights into past climates, soil fertility, and the evolution of Earth's crust. The role of clay minerals in soil formation. Clay minerals are fundamental components of soils and play a critical role in soil formation, fertility, and overall ecosystem function. Although they represent only a small fraction of soil by volume, their high surface area, chemical reactivity, and layered structure make them one of the most influential soil constituents. Understanding their role is essential for soil science, agriculture, geology, and environmental management. 1. Influence on soil texture and structure. Clay minerals are the finest particles in soils, generally less than 2 micrometers in diameter. Their presence significantly influences soil texture, which determines water retention, aeration, and root penetration. Unlike sand or silt, clay particles can bind together to form aggregates, which improve soil structure. Well-aggregated soils allow for better movement of water, air, and nutrients while preventing compaction and erosion. In contrast, soils with very low clay content often have poor nutrient retention and water-holding capacity, making them less fertile. 2. Cation exchange capacity and nutrient retention. One of the most important functions of clay minerals is their cation exchange capacity. Clay surfaces carry a negative charge due to the substitution of cations in their crystal lattice. This allows clay minerals to attract and hold positively charged nutrients, cations, such as potassium, calcium, magnesium, and ammonium. These nutrients are readily available for plant uptake, making clay-rich soils more fertile compared to sandy soils. Different clay minerals have varying cation exchange capacity values. For example, montmorillonite, smectite, has a very high cation exchange capacity and can store large amounts of nutrients, but it can also swell and shrink with moisture changes. Kaolinite has a lower cation exchange capacity but provides structural stability and is less prone to shrinking. 3. Water retention and soil moisture regulation. Clay minerals are highly hydrophilic, meaning they can attract and hold water molecules between their layers. This property is crucial in regulating soil moisture, especially in arid and semi-arid regions. Soils rich in clay can retain water for longer periods, supplying plants during dry spells. However, excessive clay content can lead to poor drainage and waterlogging, which can limit oxygen availability to plant roots and microbial life. 4. Buffering and soil pH regulation. Clay minerals act as natural buffers in soils, stabilizing soil pH against acidification or alkalinization. Their negatively charged surfaces can absorb hydrogen ions or hydroxide ions, moderating rapid changes in soil acidity. This buffering capacity helps maintain an environment suitable for microbial activity, nutrient availability, and plant growth. In soils with low clay content, pH can fluctuate more rapidly, affecting fertility and crop productivity. 5. Soil formation and pedogenic processes. Clay minerals are both products and drivers of soil formation, pedogenesis. They form through the weathering of primary minerals, as described in earlier sections, and accumulate over time to influence soil horizons. For example, in tropical regions, intensive weathering produces kaolinite-rich soils, laterites, with low nutrient retention. In temperate regions, smectite and elite clays dominate, contributing to higher fertility and structural development. Clay minerals also influence horizon differentiation within soils. Their mobility during leaching or eluviation, downward movement with water, can lead to the formation of distinct layers such as the clay-enriched B horizon. These horizons are key to understanding soil classification, fertility, and management. 6. Role in soil microbiology and organic matter interactions. Clay minerals provide surfaces for the adsorption of organic matter, which protects it from rapid decomposition. This interaction is critical for maintaining soil carbon levels, supporting microbial communities, and enhancing nutrient cycling. Microorganisms often attach to clay surfaces, where they break down organic compounds, releasing nutrients back into the soil system. In this way, clay minerals are essential for sustaining soil life and ecosystem productivity. 7. Impact on soil erosion and stability. Soils with sufficient clay content tend to resist erosion better than sandy soils because clay particles bind with silt and organic matter to form stable aggregates. Conversely, soils with very high clay content but poor aggregation can become compacted, leading to reduced infiltration and surface runoff. Effective soil management often relies on balancing clay content, organic matter, and structure to minimize erosion while maximizing fertility. Summary. In essence, clay minerals are indispensable to soil formation and function. They influence soil texture, structure, water retention, nutrient storage, pH buffering, horizon development, microbial activity, and erosion resistance. By controlling these properties, clay minerals determine the fertility, stability, and overall productivity of soils. Their study is therefore critical not only for understanding natural soil processes but also for sustainable agriculture, land management, and environmental conservation. Environmental importance of clay minerals. Clay minerals, despite their microscopic size, have a profound impact on environmental processes. Their unique physical, chemical, and structural properties make them essential in controlling soil behavior, water quality, pollutant transport, and ecosystem health. The environmental importance of clay minerals spans multiple disciplines, including geology, soil science, hydrology, agriculture, and environmental engineering. 1. Soil and water retention. One of the primary environmental roles of clay minerals is their ability to retain water. Due to their high surface area and layered structure, clays can adsorb and hold large amounts of water, regulating the soil moisture content. This property is critical for maintaining plant growth, especially in arid and semi-arid regions. By improving water retention, clay minerals help prevent soil desiccation and mitigate the effects of droughts, which is vital for sustaining terrestrial ecosystems. Moreover, clay minerals influence groundwater recharge. Soils rich in clays can slow down the percolation of water, allowing it to be gradually absorbed into aquifers. This natural regulation of water movement is essential for maintaining freshwater supplies and stabilizing hydrological cycles. 2. Nutrient retention and soil fertility. Clay minerals play a key role in maintaining soil fertility by storing and regulating the availability of essential nutrients. Their negatively charged surfaces attract and hold cations such as calcium, Ca2, magnesium, Mg2, potassium, K, and ammonium, NH4, preventing these nutrients from being leached away by rain or irrigation. This capacity ensures that plants, microorganisms, and ecosystems have a stable nutrient supply. By controlling nutrient availability, clay minerals indirectly influence ecosystem productivity, supporting agriculture and natural vegetation, and reducing the need for excessive fertilization, which can have harmful environmental consequences. 3. Pollutant adsorption and contaminant control. One of the most significant environmental applications of clay minerals is their ability to adsorb and immobilize pollutants. Due to their high surface area, charge properties, and layered structures, clays can bind heavy metals, like lead, cadmium, and mercury, organic pollutants, and even radioactive elements. This makes clay minerals highly effective in remediation of contaminated soils, wastewater treatment and filtration, barrier materials in landfills to prevent leachate migration. For instance, bentonite, a type of smectite clay, is widely used in environmental engineering to line landfills and prevent toxic leachates from contaminating groundwater. Similarly, clays are used to adsorb oil spills and other chemical pollutants, reducing environmental hazards. 4. Regulation of soil pH and buffering capacity. Clay minerals have a natural buffering capacity, which helps maintain soil and water pH within a range suitable for biological activity. By adsorbing hydrogen, H, and hydroxide, OH, ions, clays can mitigate rapid fluctuations in acidity or alkalinity caused by acid rain, fertilizer application, or industrial pollution. This property is critical for preserving soil microbial communities, maintaining nutrient availability, and protecting aquatic ecosystems from acidification. 5. Role in soil erosion control. Clay minerals contribute to soil aggregation, binding soil particles together into stable structures. These aggregates enhance soil stability and reduce susceptibility to wind and water erosion, which are major causes of land degradation. Soils with sufficient clay content can retain topsoil, organic matter, and nutrients, preventing desertification and maintaining productive landscapes. 6. Influence on sediment transport and geological processes. Clay minerals are a major component of fine sediments transported by rivers, lakes, and oceans. Their presence affects sediment deposition, turbidity, and nutrient cycling in aquatic environments. By influencing sediment stability, clays play a role in shaping riverbeds, deltas, and estuaries, which are critical habitats for many species. Additionally, clay-rich sediments can act as natural filters, trapping suspended particles and improving water quality in natural water bodies. 7. Climate regulation and carbon sequestration. Clay minerals interact with organic matter in soils, protecting it from rapid decomposition. By stabilizing soil organic carbon, clays play a role in carbon sequestration, which is important for mitigating climate change. Soils with high clay content can store significant amounts of carbon over long periods, reducing the concentration of CO2 in the atmosphere. This makes clay minerals an essential component in global carbon cycles and environmental sustainability. 8. Industrial and environmental applications. Beyond their natural roles, clay minerals are actively used in environmental technologies. Bentonite barriers in landfills prevent leachate contamination. Clay liners in ponds and reservoirs reduce water loss and contamination. Adsorbent clays remove dyes, heavy metals, and oils from wastewater. Catalytic clays aid in the degradation of environmental pollutants. These applications highlight how understanding clay mineral properties can directly benefit environmental protection and pollution mitigation efforts. Summary: clay minerals are far more than mere soil particles. They are environmental regulators that influence water retention, nutrient cycling, pollutant adsorption, soil stability, and climate regulation. By controlling the movement of water, nutrients, and contaminants, clay minerals contribute to the health of terrestrial and aquatic ecosystems and support sustainable land use and agriculture. Their unique physical and chemical properties make them indispensable for environmental management, remediation, and conservation efforts.